Okay, ladies and gentlemen, we're going to take a look at exponential graphs and give you an idea of what exponential graphs are. We've studied, what? They do, they look like a J. How many of you guys studied J curves in biology this year? I believe Ms. McNally described them that way. I'm not sure how Mr. Militex and Ms. Wheeler, or no, Ms. Wheeler, I don't think you guys have her for biology. Some of you have her for biology this year, Ms. Wheeler. All right. But they look like your J curves. So our goal is to be able to recognize growth and decay graphs, see how they compare to linear, and then use exponential models. So that's what we're looking to do today. So it's exponential if it increases or decreases by the same percent. So if it's a doubling, then it's increasing by 100% each time. If it's something like exponential decay, when they talk about like radioactive materials that have a half-life, that means it's decreasing by 50% each time. We don't have to decrease by 100%, ladies and gentlemen. We could increase by 4% each time. It just means that every time we're increasing by 4%. And so what happens with that, ladies and gentlemen, because the amount your increases changes each time. Think of it like bacteria growth. It doubles, so now I've got 2 bacteria. But then when those 2 bacteria double, it's now 4. So because the amount you're doubling, the amount you're increasing is different each time, we have these really rapid growth spurts. And here you can see this one takes off. Or we have these rapid decays, and then they slow down. But when we compare this to linear functions that we studied earlier in the year, linear had constant growth. It was always $3 per mile. So every mile, I added $3. No matter how many miles I went, I always added 3 miles. And so that's why linear functions give us a straight line, because it's constant. In exponential, the amount you're adding on each time changes because it's done at a percentage. All right? So these are what your J curves look like. I love that Ms. McNally does those. It makes my job a lot easier. All right, so now we're going to take a look at these exponential growth problems. It's considered to be growing exponentially if it increases by the same percent in each time period. So these are pretty important things to take a look at, guys. We need to know our percents and we need to know our time periods, all right? So let's take a look at what that formula looks like. We have y is equal to c times 1 plus r to the t. C is what we know as our initial amount. I don't believe I have those labeled on your notes, do I, ladies and gentlemen? All right, so these would be things that we look at. C just stands for your initial. Where C comes from, I'm not quite sure. R stands for rate. Now, if you notice, ladies and gentlemen, when I introduced what exponential growth was, I said it increases by the same percent. Percent is, or rate, I apologize, is a percent as a decimal. So it's the percent turned into a decimal. All right? So we're not going to see 4% in our problems, but we're going to see is 0.04. We're not going to see 25% in our problem, Sebastian. We're going to see 0.25. All right? So we want to make sure that we're realizing for a rate, it's the decimal turned into a percent. Okay? And if you remember, percent means per 100, guys. You're always going to divide by 100 to get that decimal value. And then T should stand out to you guys because we discussed that. T is the time. And for the majority of our problems, I cannot think of one that we look at. This is always in years. Okay? Now, there are a couple of problems, guys, that we take a look at where it talks about bacteria double every hour. And so if they tell you bacteria are doubling every hour, your time would have to be the number of hours that bacteria is growing. So you do have to be willing to read carefully to see how they're measuring their time. But like I said, for the vast majority of the problems, we're going to measure our time in years. All right, so let's take a look at what it asks you to do. It says, write an exponential model for a $1,000 deposit with a 3% interest. So notice, ladies and gentlemen, this $1,000 deposit is your C value. C is the initial amount you start with. And then 3%, it even calls it an interest rate, is our R value. Now I want you guys to notice, they haven't given you all the information, have they? What have they left out? They've left out time. And that's why this is called an exponential model. They're not wanting you to solve it yet. What they're trying to do is, can you make an equation that would let me predict how much money will I have after 5 years? How much money will I have after 10 years? For most of our models, they leave the t open. So we're going to start with y equals. You're going to write it as an equation. So it starts with y equals. I plug in my c value. So this is 1,000. Times, I need to do 1 plus r. What's, good job. Thank you, Andrew. 1.03. I usually leave it as 1 plus 0.03, ladies and gentlemen. Could we write this as 1.03? Could we do that multiplication there, guys? That's not a bad way to look at that based on what you're going to see in tomorrow's notes. But we are missing an important part of this formula. You have to include the variable t, even though they don't give you a number to plug in there. You have to have that t value there. All right, so we're going to have 1,000 times 1.03 to the t. You're going to need to read directions carefully, guys, because a couple of your problems in your homework tonight ask you to write a model. And that's all except when I want a model. You have to leave that t value out. So don't read too far into the problem simply because they give you a time. Now, when it says to find the account balance, this is what makes it a calculator problem. Okay, guys, when they ask you to find an ending amount, when they ask you to find an account balance, now you actually have a t value and can plug that in. So I'm going to go to my calculator and type in 1,000 parentheses 1.03, and now I have an exponent of 6. And yes, I'm going to use a calculator. I highly recommend most of you do. Because 1.03 to the 6th power, multiplying that out 6 times, isn't anything I want to do by chance. And so, Josh, do you have an answer or a question?
Both.
All right. Which do you want to do first? Question or answer?
Question first.
What's your question?
So especially for money problems, we're rounding up to the nearest hundred, right?
Yes, you have, because these are money problems. Did everyone hear Josh's question? And it was more of a statement. I appreciate it. You need to pay attention to what we're talking about. We're talking about money here, so that's 2 digits after the decimal point, ladies and gentlemen. I don't want the bank to cut me off. If they owe me 4 cents, I want my 4 cents. Because what's going to happen, guys, is that 4 cents I want in my account, so the next time they calculate my amount, they're taking 3% of that 4 cents. Because even though it seems silly, ladies and gentlemen, after just a couple of months or a couple of years, that 4 cents becomes a few dollars. And those few dollars then become more dollars. So that's why we want to make sure that we include all of our nickels and dimes and pennies in this. So with that question being asked, Josh, do you have an answer now for me?
$1,194.05.
Do we agree, ladies and gentlemen? I like it. I like it a lot. Any questions on that first one? This is what we call a simple interest problem, ladies and gentlemen, because they're just giving you your 3% at the end of the year. Okay? There aren't many exponential growth problems with money that deal with simple interest, but we are taking a look at a few of these. All right, now we want to take a look at an exponential model for a $20,500 deposit with a 2.75 interest rate. So keep in mind, the $20,500 is our C value, and 2.75 is your R value. Remember, ladies and gentlemen, I told you for your percent, it's the percent divided by 100. That will equal your decimal value, or that will give you your R value. So quickly at your seats, try and figure that out. We'll give you a little bit of time, and we'll call on someone to give us an answer. So compare what you're getting to your neighbors, either across the aisle or right next door. All right, Alex, what did you guys get? For the first part, just the model.
plus weight 1 plus weight 0.275.
Gee, good job. Remember, guys, you can write this as 20,500, 1.0275. I do want us to become a little more comfortable with that because we're going to need to be able to identify our growth and our decay problems from this standpoint where we've actually added those together. The reason it's 1 plus R, ladies and gentlemen, is they're giving me 100% of my 20,500. That's what the 1 stands for, the 100%. Plus, they're going to add on the 2.75%. So that's where that 1 comes from. I'm not sure if we ever take the time to introduce that to you. But now we should use the formula that Alex has. If you didn't get that, change it and use Alex's. Alex. Well, I'm trying to say it with a K with this, the K sound with the C. Alex. Alex. Answer with the 4 in there. So, Taya, what did you guys get for your ending balance after 4 years?
I got $22,849.74.
74 or 73?
74.
I did not calculate this, but do I have anyone else in an agreement with Miss Taya? And I'm assuming Cassidy checked off on you too?
Yeah, you round up.
What do you mean you round up?
Well, 73.
Yep. Yep, you're finding your rounding rules. So you're going to look at the 73 and decide if the digit after it is large enough to round it up. And because it's a 5, Taya rounded up to a 4. Beautiful. Ladies and gentlemen, is that the last column on the front side? All right, let's turn around and take a look at the back side. Ladies and gentlemen, remember I mentioned to you these monies are what we call simple interest? And we don't use simple interest with a lot of money problems. Simple growth would be used if we were looking at populations. So if we were looking at how a population increased, we would use a simple formula like that. What we're going to use, ladies and gentlemen, is what's called compounded interest. And this is what banks use. So any of you that have a savings account already or a checking account that draws interest, your bank uses what's called compounded interest. And what that means is the interest is added at different times throughout the year instead of just one time at the end of the year, which means my money has a chance to grow every month. All right? Now, it's not growing by a large amount each month when I put it in the bank, but it grows. I get a little bit more money every month. And so we take a look at that formula. Here's what we have. Now, this looks very similar to what we started with, correct, guys? What have we added in there? What's different? This n. Notice R is being divided by n, and then n is being multiplied by t. And so I do believe you guys already have all of these, correct? So n is now the number of compounds per year. So we're going to see things compounded quarterly. How many times do you think we compound something if we do it every quarter? Well, how many quarters are in a dollar, ladies and gentlemen?
4.
4. So if I compound quarterly, n is going to be 4. What about semi-annually? How many times per year is something that's semi-annual? Twice per year. All right. Monthly. How many times per year if I do it monthly? 12, because there's 12 months. What if I do it daily? 365. Even though we know this is a leap year, we're going to base our model on 365. And what's the other one? Weekly. What if they did it weekly? 52. Write that down. Weekly equals 52. You guys did really well with all the other ones I asked you. Weekly is 52. Because I don't take a lot of time here right now, ladies and gentlemen, to go through every possible scenario of compounding, but that's what those ends are. This becomes very much a calculator-driven problem, ladies and gentlemen. Dividing your rate by a value and then raising it to an even larger exponent, we need to work with that. You do need to have some sort of calculator out. So those of you that don't have calculators, please quietly go back to my desk. In the middle of the desk drawer on the right-hand side, get a calculator out. All right, ladies and and gentlemen, we're going to determine the amount of money in an account in 2015. I may have to start changing some of my notes because we now have gotten to 2015. If $500 is invested in 1990, it's compounded quarterly at a rate of 6.5%. So there's a couple of things that are really important here. I have my C value of 500. I have my rate of 6.5, which we're going to turn into a decimal. I have my N value of quarterly. How much is quarterly going to be? 4. But do I have a T value yet, ladies and gentlemen? My time is not 2015. Remember, T is the number of years. So how many years from 1990 to 2015? 25. If you have to subtract, you may need to do that. That happens a little more often, ladies and gentlemen, in these compounded interest problems, is they give you a beginning time that you start your investing and then an ending time. And that's what you'll all eventually get to, because eventually you'll start working, you'll get a real job, you'll start investing money, and you'll know when you want to retire. And so you'll put a date on that, and you'll look at how long am I going to invest my money so that I can finally retire. After 17 years of teaching, I'm ready to start talking about that. All right, so ladies and gentlemen, if we take y equals, it still starts with C, so we have something pretty familiar. We're going to have 1 plus, and this is where I would suggest, ladies and gentlemen, keeping it in formula form. So we're going to have 0.065 divided by 4, and then my exponent is going to be 4 times 25. I put parentheses around that, ladies and gentlemen, because depending on what type of calculator you have and what mode it's in, you're going to have to do that 4 times 25 in parentheses, or actually multiply it out, because 4 times 25 is a pretty easy problem to do in your head. So I'm going to show you guys what this is going to look like when I type it into my calculator, and show you what it looks like when you don't have to use parentheses. I don't think I can show you guys what parentheses has to look like because of this setting my calculators in. So we start with 500, am I correct, guys? And then is that the right C value, guys?
Yeah.
Okay, and we have 1 plus 0.065, am I correct? Divided by 4, and then I'm closing the parentheses off. So that doesn't look a whole lot different from what we wrote, does it, guys?
Hold on. 6.5 divided by 4.
0.065. So remember, you have to turn the 6.5 into a decimal.
Oh, yeah.
Because remember, it's always your percent divided by 100. Guys, I'm going to hit the caret key on my calculator. But notice on my calculator, it doesn't put the caret in there. What happened to my screen when I hit caret? It went up to the exponent. And so what that means now, guys, is my 4 times 25, this whole thing is going to be in the parentheses, or up in the exponent. I don't have to use any parentheses. I can hit enter, and I'm good to go. I'm going to have $2,506.26. Now, let's see, I think I will try and do this for you guys. If I type this in, 500 times 1 plus 0.065 divided by 4, 2, if, ladies and gentlemen, if when you hit the caret key, it actually makes a caret, what that means is it's not putting things into the exponent position. So this display is going to need parentheses 4 times 25. All right? So you just have to know your calculator. You have to know what mode it's in. Those of you that have to use your phones, you're going to need to probably do the multiplication ahead of time in your head, because I'm not exactly sure how to use parentheses on a cell phone. All right? But either way, notice, guys, did I still get the exact same answer there? $2,506.26. Is that what we got the first time, guys? I don't have it up on my screen anymore. Okay, so make sure you know the difference between using parentheses and not using parentheses. All right? So let's go back.
Years.
Well, all right, so ladies and gentlemen, let's take a look at the next example. It says determine the amount of money in an account in the year 2050. And this should be our last example. If you invest $1,000 in the year 2000 in an account that earns 8% interest, if compounded the following ways. Monthly, what's our end value going to be? 12. And for semi-annually, what's our end value going to be? 2. And so we're going to have 1,000 times 1 plus 0.08. Remember, ladies and gentlemen, simply because you see a decimal doesn't mean that it's in decimal form. You have to divide it by 100. So 0.08 divided by 12, because that's for our compounding formula. And then my exponent is going to be 12 times, how many years am I investing the money? 50. Now, before you guys go too far, I want to once again show you guys how you can use your calculator to be a little bit smarter and work a little bit, work for you. Is it 20, how much are we investing, guys? 25, or 1,000 times 1 plus 0.08 divided by 12 to the, I didn't change my mode, 12 times 50, correct? And we hit enter and we get $53,878.18, correct? Now, ladies and gentlemen, some of you are working ahead of me instead of staying with me, and I really would like you to stay with me because I'd like to show you some things about your your graphing calculators that do make life a little bit easier for us. Are we all getting $53,878.18? Right here.
Oh, wait a minute, no,
Okay.
I've added 0.
The only thing that's going to change for part B, ladies and gentlemen, is the 12s, correct?
Yep.
So what I'm going to do, ladies and gentlemen, is instead of retyping all of that in, hit second and then enter. What happens when I hit second enter? It brings up the formula. And so now what I can do, guys, because this is flashing here, I can cursor back. I don't want 12, I want 2. Don't hit clear. Guess what clear will do for you? Cancel everything. What do I want to do? I want to delete the 1, so hit delete. Delete. I like that option, guys, because if I know I get the formula typed into the right way the first time, if I do second enter, it leaves a whole lot less room for errors. And for some of you, that's what your mistake is going to be. Typing in, oh, I typed in 0.8 instead of 0.08. Dude, if I do it one time and focus one time, I'm able to get it correct the second time. And so now we get $50,504.95, which is what I should suspect, ladies and gentlemen, because when I compound it only twice, I'm not getting as much money as quickly as when I compound it 12 times. So this is why we have this compounded interest, because I can get more money more often. All right? Ladies and gentlemen, any questions over what we just did today? I mean, I guess most of your questions are probably going to come with the calculator, so we definitely need some in-class work time. So if we take a look at what your agenda said, ladies and gentlemen, for some reason I have a blank screen. Your agenda has page 480 to 41, number 6 through 24, and then the extra problems with 8.5. Can I please have you guys listen? Tomorrow on the agenda, it says page 488 and the extras worksheet. The way your extras worksheet works out, ladies and gentlemen, 8.5 is the top half, 8.6 is the bottom half. So the worksheet I hand you today, you're not only going to need today in class, when else are you going to need it? Tomorrow, because I did not make 60 extra copies for those of you who lose it. So please keep track of that. The sub will grade the top half with you tomorrow, but will not be collecting or recording any assignments from you. Okay? So while you guys are waiting for the worksheet, you can get started.